Good afternoon, good morning if you're on the West Coast, and good evening, everybody. We're really excited to welcome you today for our office hours number 30. My name is Sasha Zelenovic, and I manage our developer marketing here at Red Hat. With me is also Michael Goin from Red Hat. Michael is also a vLLM commuter, a very familiar face to everybody here. Michael and I run these office hours. If you're new, we love having you here. Please keep coming back. And if you've been here for a while, I see a lot of familiar names. Welcome back. Today we have Chen Zhang joining us. Chen is a postdoc at UC Berkeley. She is also a vLLM commuter, and she spent a lot of time working on the hybrid memory allocator architecture in vLLM. And today's special session will focus on that, so you'll be in great hands. I know that we special sessions and every week here, and that's great to have. But I do want to remind everybody that this is a completely open forum. So if you have any questions, any feedback about vLLM and inference in general, it doesn't have to be about a special topic. Please feel free to either use the chat or raise your hand. If you're watching us live on YouTube or X, you can feel free to comment. We pay attention to all of these channels during the call. So just let us know, and we'll be here for you. So Michael, please go on the next slide. So as you guys know, we are recording this meeting. The recording will be live on YouTube minutes after the call. So if you want to share with your colleagues or review the content again, you totally can. Michael, did you share the slides, by the way, yet?
Yeah, I pinned the message in the chat.
Oh, great. Okay, good to see. Thanks. So slides have been shared. You can follow along if you want. You can also share those public. Always nice to have. So one good place to always ask questions, follow-up questions or questions in general is the vLLM developer Slack. It's linked in those slides. So if you're not in there, please join us. We do have our own office hours channel in the vLLM developer Slack. So please join that too to stay up to date with, pre-recordings, upcoming meetings, etc. We would love if you can help us spread the word. So if you're active on social, and if you're doing or not, we would love if you can share a live link. So we are streaming this live on YouTube and on X. You can just copy those links and post them, or just repost our live sessions as they're happening right now. That would be amazing. And then one quick thing before we go into our fun geography exercise, we do have a handful of meetups planned. In the next few weeks, we have Seoul, Korea, Jakarta, Indonesia, and Shanghai in China. All of them are linked right there. I know there's probably not too many people from those regions or from those cities currently on the call. Maybe you'll see the recording. But if you have colleagues or friends, feel free to send them the invite. Seoul is definitely booked up. It was one of our fastest growing. We had 150 people register in 24 hours. But if you're on this call and you want to attend, there's probably something we could do. We're also planning Boston and Toronto. We don't have registration pages yet, but they will be going up shortly. But that's happening in September. Towards the end of September. And then we're also looking at EMEA, discussing Paris, London, Austin in Texas potentially. So there's a lot of meetups. If you would like to bring the meetup to your city, reach out to me. You can find me in Developer Slack. You can message me right now. We would love to collaborate with you. I think squeaky wheels definitely get some attention here. So before I pass it over to Michael, one fun thing that we do here is we open up the chat right now. So if you can please open up your chat and just tell us where you're dialing in from. You can see the flags that have raised there that have been here in the past. We definitely cover most of the geographies. This is just the people that spoke up. But, oh, Jordan, I don't think we have a Jordan flag. Nice, that's awesome. Love adding new flags. Hi, Michael in Boston, Berkeley, Dallas, Texas. Wallace, welcome. 30th time maybe, from Rio, Brazil, Houston, Texas, Brazil. Max, you've been here 29 times probably, so hats off to you. Hopkinton, Mass, Switzerland, awesome. Concord, Massachusetts, North Carolina, Florida, Oregon, wow, active audience, Canada, Chile, Brazil, New Mexico, California, Virginia, Silly Willy. All right. Thanks, guys. It's never too late. If you're in New Hampshire, hi, Brian. If you want to add where you're from, Texas, just let me know and I'll add that flag. And I think Jordan will be added next time. But awesome. Welcome from Toronto. Okay. Michael, I'm going to pass it over to you.
Sure. Thanks a lot, Sasha. And good to see everyone again, see all the friendly faces. So today we have a decent bit to cover. But unfortunately, we haven't had a vLLM release since the last office hours. We're working very hard on getting that out as a stable branch. And if you've been contributing, you probably have seen that the CI has been pretty unstable. So we've been working a lot recently to stabilize that and improve processes going forward. I'll touch a bit on that. But I do have some events and blogs that have come out recently that we'll briefly cover. And then, of course, later in the session, we'll have Chen covering the hybrid memory allocator, which is a really important piece of infrastructure in vLLM that's going to, or that does allow us to support modern LLM architectures much more easily, as increasingly more state-of-the-art models have non-uniform attention layers, and thus means we can't manage their memory in a uniform way for all the layers. Like think Llama 4 and the recent GPT OSS, and of course the many different state space Mamba style models. Following that, we will have a deep dive into Mamba and specific hybrid model support as the next session. And then we're hoping to have a session on really doing a deep dive into inference scheduling for distributed inference in production with vLLM and LMD, all the different types of scheduling. So a really good deep dive if you're trying to scale up your workloads efficiently. So to kick things off, just a quick primer on vLLM if you aren't familiar with the project. It's the fastest growing de facto standard in open source model serving. It's been around since early 2023 and came out with the page detention paper. And since then, it's had very steady, consistent, rapid growth as a very popular open source project with over 50,000 GitHub stars and I think now over 1,300 unique contributors. It's in the PyTorch, it's in the Linux Foundation, and specifically under the PyTorch Foundation, and it supports 100+ different model architectures and many different hardware backends with that as well. So that's part of the reason why vLLM has become so popular is how easy it is to use, and then of course how it serves as a software interface for the many different types of models and hardwares that are released and want to be used. So because of that software middle ground that vLLM is able to offer, as it makes it a very fertile place for inference research. So many MLSys papers build on top of vLLM, fork it, integrate some new scheduler, some new mechanism for optimization, and those research papers pull into vLLM over time, both from research, also from industry, and of course from the variety of people in the community. And then of course the many different hardware accelerators have found vLLM a really great project to support and develop their hardware backends for. So of course it gets great performance on NVIDIA, trying to be and close and competitive with like Tensor TLM that's built for NVIDIA only, but it also does well on like AMD GPUs, Google TPUs, AWS, Intel, Huawei accelerators and CPUs and more hardware accelerators than that even. And of course, it doesn't just support text-only large language models. It's also expanded over the years to support multimodal models, hybrid attention models, as we're going to talk about today, embedding encoder-only models, and then, of course, reward models, which are like critical for modern RLHF workflows, where vLLM is a part of the RLHF workflow, as you need many inference rollouts to train your models within reinforcement learning. And then more on the software infrastructure side, because of the abstractions vLLM offers in its model definitions, we're able to support many different types of quantization of the weights, the activations, supporting those with custom kernels that are performantly written in Cutlass, Triton, Torch Compile, and other languages. Then, of course, many system-level inference optimizations for more efficient scheduling or forward passes like chunk prefill, automatic prefix caching, multi-layer batching, supporting speculative decoding methods and disaggregated prefill for cluster scale inference. And then, of course, scaling beyond single node deployments into multi-device and multi-node with the many different types of parallelism available for inference, tensor, pipeline, expert, data parallelism. So yeah, really meant to be a whole bundle of tools that can be used together for scaling your inference. So a little bit of a reason why Sasha and I are here from Red Hat. We contribute a lot to Red Hat. As we mentioned, I'm a committer, just as Chen is. We work a lot on the performance features of vLLM, compression integrations, many production level features for our enterprise users of vLLM, and of course, squashing any system overheads, CPU overheads, and overall just work on a lot of things inside of vLLM that you can hopefully see from here. So now I want to cover some of the things that are new since the past 2 weeks. There was a really great Beijing meetup in vLLM. As Sasha mentioned, there's going to be one in Shanghai later this year, or sorry, this month. But the Beijing one was a knockout. Tons of developers, engineers, everyone there. Lots of fun signs but most importantly, talks. So if you're interested in seeing an overview of what some of the different companies that talked about there and their various slides and topics, I recommend checking out the PyTorch blog covering this. But as you can see, there's a wide variety of stuff mentioned. Hardware backends like Huawei Ascend, optimizations for key leading edge models like DeepSeek and Kimi K2, and of course, scaling into large scale inference with disaggregated prefill decode. So recommend checking that out if you want to get a bit of a deep dive in what's new and how people are using vLLM. And then I also want to touch on, the release just last week. I can't believe it was not that long ago. But yeah, OpenAI released their first open source model in several years, open source LLMs. And vLLM was obviously had day zero support for that and was reference implementation serving for that. So I recommend checking out the vLLM blog, our deployment recipes, where we detail how to deploy the model, from A100s to B200s, the official OpenAI cookbook that talks about, of course, how to deploy the model in vLLM, but also how to use it, particularly for its specific like reasoning and agentic capabilities. And then I also want to give kudos to Artificial Analysis, which is a really great website and service for benchmarking the many different API providers for both closed source and open source models. But as they were validating the accuracy of the different hosted endpoints of GPT-OSS, they started using vLLM as the baseline to see which ones were lagging behind the open source reference implementation. So this was really interesting to see, and interesting to see what providers maintained accuracy better than others. So hopefully it'll serve to promote better standards overall and make your money worthwhile for valuable tokens. Another blog I want to highlight is this CUDA debugging blog written by Kai Chow in collaboration with the NVIDIA team. There's, if you've ever worked on CUDA kernels, developing these or trying to build CUDA kernels from source, I'm sure you're very familiar with some of the illegal memory accesses that are mentioned here. As someone that's worked a lot on CUDA kernels, there was a lot of stuff in here that I hadn't known about, even after working many years on this. So there's a lot of great CUDA, great little bits in here to help you debug and understand and just grow your understanding of CUDA, even way beyond vLLM. So if you're interested at all, I recommend reading about some of these tips and tricks from the experts and seeing if you can add it to your tool belt to make your life easier in the future. And lastly, from the vLLM project side, I want to talk directly about vLLM CI. If you've been trying to land PRs over the last week or two, you probably know how unstable and failing it's been. We've had to force merge many PRs to land in just because there's lots of known failures on main for over a week. Sort of in the scramble for GPT-OSS, there were a lot of scrambles to get things in. and these kind of failures become compounding and just build the wrong culture around keeping CI green. So yesterday we essentially paused all non-essential merges to main and only focused with a wide group of people to fix main and fix the very many tests. And I can say now of this morning, things are in a pretty green state. That's great for now, but we want to make sure these things are better taken care of in the future. So we're working on public dashboards and to improve observability and maintainability, so that you as a contributor, as someone that's making your PR and you see all these failures, hopefully there's one place you can look at and see, okay, are these known failures? It's not related to my PR. I shouldn't be so worried. Maybe you can help. Of course, it'd be great to get help with the efforts to fix these things, because we never want main to be failing. But overall, we don't want contributors to be in a place where they're putting up their PRs and they're confused why there's failures or whether it's related to their work or not. We want to take accountability and try to make these issues as transparent as possible. And then another big effort that's going to be ongoing, I think, for the coming months, is really bringing the cost, sure, but also the speed of CI down. For instance, at some points, building the initial Docker build, essentially preparing the pre-built image for vLLM to then start testing took almost an hour. So that means before any tests are run, it takes an hour to start running tests, and maybe the tests take an hour each. So you're waiting 2 to 3 hours to get your status back, and we think this is really unacceptable, particularly if you're just editing Python. We think if you're editing just Python code and nothing really complex needs to be compiled like C++ or CUDA, you should be able to get your build done within minutes, and then hopefully the end-to-end CI should run within less than half an hour or something. So we're going to make a concerted effort to improve the end-to-end time of CI, to improve the iterations, so people don't have to wait so long and be so confused about why everything takes so long and why it takes so long to get back. We think this is a really key thing to work on to improve the amount of developers that can contribute to vLLM effectively, the ease of developing and contributing to vLLM, and just want to say we take this seriously. We hear you, and if you have any ideas or want to help, please reach out. There's a SIG CI channel in the vLLM Slack, and many other sub channels where we're talking about things like this. And we of course would appreciate your help. Anything you can do to prune back tests or help try to speed up things, yeah, we appreciate it. So that's all I have to talk about. Thanks for letting me ramble. Now I'll hand it off to Chen to cover our very interesting special topic.
Okay, thanks, Michael. I'm Sherry.
We can see your screen.
Yeah. Is it working now?
Mm-hmm.
Okay.
Yep.
Okay. Hello, everyone. I'm Chen Zhang. I'm a postdoc at UC Berkeley, and I get the effort of the Hybrid Memory Allocator design. So first, what is it? From nowadays, the LLMs has very longer and longer context because we want to support many complex tasks like the chain of thought, like multi-turn to coding, and visual analysis. So, given these tasks, the context can sometimes reach very long. For example, sometimes even can reach about 1 million tokens. And then the KV cache size becomes a new concern, because if we have 1 million tokens, then the KV cache size may reach, for example, about 150 gigabytes. This is calculated with a quite standard LLM architecture with 8 KV cache, 128 hidden size per head, and 40 layers. As a solution, recent models usually use sparse attention, like the sliding window attention, to reduce the KV cache size. And here is the architecture of these models. They usually use a heterogeneous architecture mixed with both sliding window layers and full attention layers. For example, you can see the figure B. It is a 6-layer model with full attention layer, and then followed by 2 sliding window layer, and then another full attention, and followed by another 2 sliding window layers. The goal of this architecture is 2 parts. First is to use some sparse attention layers to reduce the KV cache size, and the second is to still keep a few number of attention layers, so that to preserve the long context processing ability. For example, there are many models that use this architecture. For GPUSS, Gemma series model, and Cohere models, they usually use full attention plus sliding window attention. And there are many models mix full attention with a state space model, like the Bamba, Jamba, Minimax, and also Gamma 4 mix full attention with a special type of sparse attention. They call local chunk attention. And these models have give new challenges to the design of the KV cache management system. The problem can be divided into 2 parts. First is memory allocation and also the prefix caching. For the memory allocation part, now the KV cache consumption of different layers can become different. For the previous models, it is a quite regular memory allocation pattern. All layers have the same hidden size, and all layers have the same number of tokens. So the page attention algorithm works pretty well. However, in current new LLMs, the number of tokens in different layers becomes different. For example, sliding window attention layers only need the last few tokens KV cache, while the full attention layers need the KV cache of all tokens. And also, sometimes the hidden size, the KV cache hidden size per token is also different. For example, for models mixed with Mamba and full attention, the Mamba layers, the state size of Mamba layers can be pretty big, much larger than the KV cache per token in full attention layers. Then it gives new challenges to the memory allocation system, because we now need to allocate different size KV cache, and also to minimize fragmentation and to be compatible with all the infrastructure in LLM inference, like the kernel libraries and the external KV cache, external KV connectors, such as that. And for the prefix caching part, there are also new problems, because the cache hit rule of different attention layers is different. For example, for sliding window layers, we only need the last few tokens for cache hit. We don't need all the tokens in the prefix to remain in the cache. Then there is some problem on the cache management. Okay, first let's talk about the KV cache allocation. To begin with, I will recap of the V0 block manager. It only considers the standard models with only full attention layers. So it divides the whole memory into several blocks. Each block refers to the memory for all layers of 16 tokens. And then for requests, it just computes the number of blocks needed based on the sequence length. For example, here is a request with 80 tokens, then just allocate 5 blocks. It is a very great and very simple algorithm if the models only contains full attention layers. But Nowadays, the models have more sliding window attention layers. Then there will be memory waste if we still allocate the same size memory to we allocate the same memory to different layers. Then we decided to design the new hybrid KV allocator. The key design decision of this workflow is first, we will still keep the physical memory size per block the same, so that we don't need to handle external fragmentation, and it can help us to integrate with the external PD and KV cache storage framework. So the second thing is still work in progress. It is doable. And the second, this gives some restrictions, but as we need to allocate different size of memory to different layers, then we will allow different layers to have different number of blocks. Oh, I see a comment. Okay.
Yeah, there's a comment on why reducing the block size to smaller tokens is a bad idea here. Doesn't it address the memory fragmentation issue?
Okay. Reduce the block size to smaller tokens. Actually, it doesn't. Let me go back to that slide. The key problem is not about how many tokens in each block, but it is only about the sliding window layers don't need the KV cache of the early tokens. For example, even if the block size is 1, then we will allocate 80 blocks, and the first 48 blocks will have memory waste. I'm not sure whether it answers your question.
Yeah, I think it's clear to me. Just to add, I think like making the block size too small also has an impact on the efficiency of the attention operation itself, on the ability for the attention kernel to deal with the discontinuous memory.
Yeah. Okay, let's go back. The key design decision to ensure the memory allocation flexibility is to allow different layers to have a different number of blocks. Then we can have a very straightforward idea. Just allocate blocks for each layer. Now we define the block, one block as the KV cache of 16 tokens of one layer. Then for the given model with 2 full attention layers and 2 sliding window layers, we just allocate 5 blocks to each full attention layer, allocate 2 blocks for each sliding window attention layer. In this design, we will have no memory waste. But the problem is that it needs to call the allocator for each layer, and it will have pretty large overhead. For example, for GPU-ICS 120B, it has 36 layers. Then we need to call the allocator 36 times and introduce 36 times overhead compared with the original algorithm. And to solve this, we find, okay, not sure if it's feasible, but very possible. Not sure if it's feasible, but is there any possibility of variable size blocks? Okay, that's also possible, but I think the major concern is about it's about managing the external fragmentation between these different size blocks. As long as we have different size blocks, we need to manage the fragmentation, and I think the external and when integrated with the KV connectors, the PD framework will be unhappy about that. Okay, and then how to go back to the slide, how to reduce the overhead. We find that very lucky we usually have an n/1 ratio between the number of sparse attention layers and full attention layers. For example, in GPU-OSS, it has 18 sliding window layers and 18 full attention layers. Then the ratio is 1:1. And for Gamma 4, it has 36 local attention layers and 12 full attention layers. Then the ratio is 3:1. And we can make the layers into n+1 groups and do the allocation for each group. For example, if we have a model with 20 sliding window layers and 10 full attention layers, we can just it's a 2:1 ratio. We can where n equals to 2. Then we can divide it into 3 groups. The first group is for the 10 full attention layer. The second one is for the first 10 sliding window layers, and the third one is for the remaining 10 sliding window layers. And we can just allocate blocks for each group. For the first group, allocate 5 blocks. For the second and third group, allocate 2 blocks for each. And each block is defined as 10 layers and the 10 layers and the 16 tokens. Okay. Another question. Is there a notion about how to code KV segments and prefetching back to HBM? Or is I think we are not talking about CPU flooding, which is an important topic. We are still working in progress.
Yeah, this all assumes that your blocks are in HBM.
Yeah.
Yeah.
But in real world, the things is not always that happy. For example, if for the above algorithms, actually we are making 2 assumptions to ensure that each block has the same physical memory size. The first is the great n/1 ratio, and the second is the QX hidden size per token is always the same. But both of them can be broken. First for the ratio, there can be there are some models with bad ratio. For example, in JAMA 327B, it contains 52 sliding window layers and 10 full attention layers, and we can pad it to 16 sliding window layers and 10 full attention layers. And also there are some layers, some models that have different KV hidden size. One major example is the Mamba model, where the Mamba state can be very, very large. And our main idea is to increase the block size of full attention layers, so that the physical memory per block of the full attention layer becomes larger, and match the size of the Mamba state size. Then the block size will be about several hundred. But based on our benchmarking, it works fine now. Okay, to clarify, is the pattern implemented now in vLLM? The pattern, yeah, the pattern is implemented, but it's not in the single type manager. It is implemented during the get KV cache config. Okay, let me type. What about a custom heap allocator for from fixed size pool and blocks for more standard attention? Okay, the problem is now we have 2 pools. Then how to divide the memory into these 2 pools? For the member, a background I want to add is that we want to also support the prefix caching of member state, so that we need to cache unknown number of member states, and then it will have some problem of the fixed size pool design, because for short requests, let's say for short requests, maybe the pool size of the member and the full attention would be similar, because their memory consumption is similar. But for long requests, maybe we need a pretty small member state pool and a very large full attention pool. And but without the information of the sequence length, we can't decide the pool size of the two parts. You can make blocks from the heap. If all blocks are allocated from the heap pool, you can free blocks back into the. Then in that memory, then what will that memory pool be like? Will it be a fixed size of blocks, or it is just like the general memory allocation system without partitioning the memory into blocks?
Can I just raise my hand and ask a question? Or just,
Okay.
so I still agree that there should be two fixed size pools, but they don't have to be fixed size, or there should be two different pools, like blocks and maybe this other amorphous thing, right? That could be a heap pool, but there doesn't have to be a strict boundary between those two things. Like essentially the block pool size could grow and you could steal memory from the heap pool, or you could shrink the block pool and grow the heap pool, right? So that like you're working with like ISO amount of memory, but you're just changing the amount each of those different pools has as a function of like your load. It's still obviously like fragmentation is always going to be an issue here, but it would just give you like really nice flexibility, because you could use like some sort of like red black, or like some sort of best fit allocator in that heap, so you could have relatively reasonably control the fragmentation there a little bit, but still be able to then fall back to your regular block patterns for standard attentions. I don't know, it's just an idea. It's something that we could certainly like scope out.
We actually have talked about this, and the major concern is we don't want to implement too complex allocator inside the vLLM.
That's fair. That's yeah, absolutely.
Okay. Let me continue. I think that I have finished this page just for the bad ratio, then path layers, and for the different KV hidden size, we just increase the block size of for attention layers. Okay, then it's the second question about prefix caching. For given a new request, how to detect the cache hit length, and then given when we need to evict, which block should we evict? Both of them are challenged by two things. First is there are different layer types, and we need to customize the packet rule of different layer types. And the second problem is we need to manage multiple layer types at the same time. Okay, sorry. And first is how to detect the cache hit length. Let me go through one by one. First is the full attention. Finding the cache hit sequence of full attention is quite simple. Just iterate the blocks from left and right and stop when one block is not cached. For example, if here is a request with the first 7 blocks cache, then the cache hit sequence is 7 tokens. And then for sliding window attention, the longest length is the cache hit sequence is the longest length with at least window size -1 tokens. For example, if we have window size 4, then we only need the last 3 tokens to be cached. For example, in this example, we can regard the cache hit sequence as 10 because for the following tokens, we only need the QB cache of the last 3 tokens to generate the QB cache of new tokens. And how to get this sequence? We just scan the request from right to left until we find the first match with at least window size -1 tokens. And then the second, then we come to the heterogeneous models with full attention plus sliding window attention. Then our algorithm is first check the cache hit sequence of full attention blocks, scan the full request from left to right, and find the cache hit sequence of the full attention layers. Then we try to find the cache hit, the longest cache hit of sliding window layers under that length. We just scan the sliding window cache from right to left, starting from the 7th tokens, and returns the longest sequence set with at least 3 blocks. In this example, we scan from the 7th tokens and the 6th tokens, and then we find the cache hit sequence is 6 because we have token 3, token 4, token 5 cached. The good part of this algorithm is it can work when there is no cache hit. It don't need to scan the full sequence, and so it don't introduce much overhead for for scenarios that don't cache hit, that prefix caching doesn't work. And the sad part is it assumes the model only have to have full attention layer plus only one type of smart attention layer. This is an assumption that is held by most existing models. We will upgrade the algorithm if we find there are more important models that doesn't follow this pattern. And then the cache eviction, we choose to have one LRU queue for all different groups, and define the recent use in this recent use as the time to freeze at blocks. It is a functional algorithm, but we need to admit that it can be further improved. And here is the benchmarking result. First, this hybrid allocator can improve the throughput because it can reduce the QB cache size per request, and so that the engine can batch more requests and result in larger throughput. And here is the number for Gamma 3 12B model. And it can also give the opportunity to support longer max model lengths. For example, Gamma 4 have a very crazy 10 million context lengths. And with hybrid allocator, we can run support the full context length within our 8H200 node. But without the hybrid allocator, we have to reduce the max model length when deploying in one node. And there, it is still in the early stage, and we have many to-dos now. For example, I will give some most important things. First is the prefix caching of member layers. It is doable, but not supported in the main branch yet. And we are also working on integrating it with QB connectors. And someone reported that it can have some overhead. especially when the sequence is short, and we are also working on that. And to reduce the complexity of implementation, we have made many small assumptions based on the current model architecture. This can maybe break in the future, and we will then upgrade the implementation to improve the flexibility. Okay, that's the part I'm sharing, and feedback is welcome.
Yeah, thanks a lot, Chen. There's already been some nice questions, I think, along the way. But if people have more, feel free to say in the chat or raise your hand and come off mute. I guess maybe like one question I have, since no one's coming immediately off mute, is like with respect to the overhead, since I'm familiar or ran into that a bit myself, do you think there's like something inefficient about the architecture and like data structures chosen at the moment, or is it more just the implementation itself that just hasn't been super tuned for performance?
I think for the overhead come from two parts. First, we need to call the allocator number group times. Second, we need to build the attention metadata number group times. For the call the allocator number group times, I think there is a very few chance for improving the speed, and maybe we will work on improving the data structure, and the remove the overhead of each call, so that the allocation part won't take too much longer time. And for building the attention metadata for number group time, I think Lucas is working on that. Just the major idea is the main idea is for example there may be several groups with slightly window layers. Then most attention metadata attributes would be same, and only some attributes related to block ID will be different, so that we can build other attributes one time and then update the block ID for each group.
Yeah, okay, that makes sense. There's a comment from Flora. Are there future work planned from ideas for the Jenga paper?
Oh yeah, that's a paper that discusses design, and we will gradually implementing some key features from that paper. For example, maybe we will improve the catch hit of sliding window attention based on that algorithm, or maybe some parts if the community think it need to do. And the second question, how much performance efficiency we should expect to see with this? How much memory saving? Okay, the efficiency we can see this figure. This is the thing is if the model have if we run a very small model on a very large GPU, then we won't see much performance improvement because the batch size is large enough. But if the query cache size is a concern, for example, for the model, for the Gemma 3 model like this, we can only batch, for example, 10 requests or 20 requests. Then the hybrid allocator will give much larger speed up. And how much is the memory saving? It's for Goin sequence, the memory saving is similar to the ratio. For example, for a model with 20 sliding window and 10 full attention, and for pretty long context, then we can save about 60% of the memory.
Okay, there's another question. I think Sasha forwarded. Any work being done on Int4 KV cache quantization for Ampere GPUs? I think that's I may want a bit more details if like what type of quantization, because you can actually use like FP8 KV cache fine on Ampere, because we're just doing the KV cache quantization for storage and not actually for computation. But yeah, like currently there's no one really working on this. I think some Google people are working on expanding KV cache quantization, but at the moment we only support like per tensor FP8 scales. So certainly if you're interested in KV cache quantization, would be happy to shepherd help. It's just not super high on priority. The FP8 is fine. Actually, a question I had for you, Chen, on the, I guess like something that seems like inherently tied with like the memory allocator being aware of like the type of attention is like, you know, now you consider the space that's not being used by the current sliding window at the end as being like free for the current requests. I'm interested if there's been any analysis on like, of course you can reach like larger batch sizes for like requests coming in because you have more space in the KV cache, but maybe you are like reducing the amount of cache hits you get for prefix caching because you're like freeing up blocks like too quickly that could be reused by other matching requests coming in, effectively like shortening the prefix caching you could hit.
Yeah, yes, I already aware of this problem, and I'm thinking that for the GPU memory, we should maximize the throughput, and I'm waiting for the CPU KV cache being implemented, and maybe we can perform a better memory management, the KV cache eviction in the CPU side. That's my plan.
Okay, cool. Yeah. And yeah, Ryan said this is where offloading via the connector for sliding window could be valuable. Yeah, I mean, I agree.
Yeah, so I have to admit that I have I don't have a very specific idea on how to implement that. I just have some random ideas on the support, and maybe we can discuss more about it later.
Yeah. Yeah, I'm actually curious, maybe I don't understand this properly, but when you're doing like a prefill with like sliding window attention, you like aren't actually allocating blocks like for like say you're doing some like really large prefill, you can do like 10K tokens, and you're like GPT OSS where you have like 128 token sliding window. Like, are you actually including like, is there any point where you're actually ever generating those like blocks other than like the 128 tokens at the end?
For the prefill, we need to first compute the KV cache of all blocks. Because for example, the token 1000 needs token 900, and 900 needs 800, and something like this, some dependency like this. So we need to compute the KV cache of every block. And with the current implementation, we just save all the blocks into the KV cache and free it immediately.
I see.
Yes, the next step. Because of chunk prefill, I think it won't be a very large problem.
Yeah, definitely with chunk prefill makes this less of a problem, but yeah, it's definitely interesting for like very aggressive like sliding window, I guess. But it's maybe a similar problem to like state space models where it's like
Yeah, for the prefix caching of for state-space model, for now we only allocate the one block for each request, but we are still discussing how to support prefix caching.
Yeah, you would need some like checkpoints, like clear points.
Yeah, something like this.
Yeah. Sliding window from tail to root. If you have more. Oh, that's a really good point, Ryan. Yeah. Okay. Yeah. So like obviously, if you have sliding window attention, then like, what's the point of prefix caching? Because like you're only needing to actually compute those last number of tokens. So
your prefix cache changes, right? You match backwards, and if you have a full window, you're done. And if you don't have a full window, then you have to kind of pre-fill everything. So you hope that maybe you have some of those preserved in your external caches.
Yeah.
Okay. Yeah. So that's really not a problem for like GPT OSS. Yeah. Okay. Yeah. Any other questions? We're getting near the end. Yeah, really great discussion so far. Glad we have some Dynamo folks here that are thinking very carefully about this stuff too. Okay, well, I think we'll probably call it there. Shout out to Chen for a really great presentation and description of the hybrid memory allocator. I think we'll have some docs and like diagrams and stuff like coming out as well. That's long lived in the vLLM docs website. Maybe a blog, who knows? So definitely expect more work in this space. Obviously, there's a good bit of future work that was detailed. And hope you found it interesting. So thanks everyone again for coming to office hours this week. Great seeing you as always. And let us know if there's anything you'd like us to do in the future, if you're interested in helping out and presenting yourself. And of course, stay active on the vLLM GitHub, stay active in the vLLM Slack. We're happy to hear from you and hope you have a good week.